Plate tectonics in action.
What in the world are plate tectonics? Is that like some kind of dance move from the 80s? Or like a new event in the Olympics?
Plate tectonics is the theory that the surface of the planet is divided into large plates like puzzle pieces. These solid pieces float atop the hot, liquid layer below them. They are constantly shifting around.
Specifically, Earth's surface is covered by 10 major tectonic plates, like 10 gigantic floating puzzle pieces.
Tectonic plates are pieces of the lithosphere, that rigid outermost layer of the Earth. Because they are lighter, they float on top of the dense asthenosphere below.
Because the lithosphere covers the entire surface of the Earth, that means it includes both the continents and the ocean floor. So, some tectonic plates are made of continental crust, while others are made of oceanic crust.
Oceanic crust is always denser than continental crust. Lock that into the old noggin. It'll be important later.
The point where two plates meet is called a plate boundary. A plate boundary is like the place where two puzzle pieces fit together.
Let's take a closer look at Earth's plate boundaries. Do you notice anything interesting about the places where they occur?
Step number 1 to sound detecting, my young sleuths, is searching for patterns. A pattern is a clue. Step number 2, once you find a pattern, ask yourself, what does it mean? Is there a connection to be made here? Step number 3, eat a sandwich. So, does anyone see anything here? Because I've got nothing.
Mountain!
It's like there's something right here beneath our noses that I just can't put my finger on.
Mountain!
It's maddening!
It's no coincidence that mountain ranges occur at plate boundaries. The same goes for volcanoes and earthquakes. Mountains, earthquakes, and volcanoes are all the result of tectonic plate interactions.
In fact, you can think of them like signposts. Like when you see a mountain or a volcano, you can confidently announce to your friends that you are in the vicinity of a plate boundary.
Of course, when it comes to earthquakes and volcanic eruptions, it is helpful to know that you are near a plate boundary before anything happens, so you can be prepared.
Preparedness is key. I would never have gotten by in Canada if I hadn't been armed at all times with beef jerky and a shower curtain. Young travelers, always be prepared.
So what determines if a plate boundary will be marked by a mountain range, a volcano, or an earthquake zone? Or all of the above?
Excellent question. The answer is it depends. It depends on the way the plates interact. How plates interact is determined by what type of boundary they form. Check it out.
Types of plate boundaries.
Ladies and gentlemen, the Spandex Pants Collective of Boulder, Colorado quietly presents Plate Boundary.
There are 3 main types of plate boundaries: convergent, divergent, and transform.
A convergent boundary occurs where 2 tectonic plates collide.
A particular type of convergent boundary, called a subduction zone, occurs where a slab of oceanic crust meets a slab of continental crust. Because oceanic crust is denser, it will always slide beneath the continental crust. Mountain ranges, earthquakes, and volcanoes are likely to be found at subduction zones.
Need help remembering how subduction zones work? Just remember this quirky little saying. Dolphins dive, so does oceanic crust. You're welcome.
Another type of plate boundary is a divergent boundary. Divergent boundaries occur where 2 plates are separating from each other.
Finally, we have the transform boundary. Transform boundaries are where 2 plates slide past each other like 2 people in a crowded restaurant.
In general, activity at plate boundaries can cause all kinds of stress on the surrounding rock. When the Earth's crust is put under stress by plate boundary activity, this can cause it to bend, break, and even to quake.
It's just like on that episode of Nicole and Herman when they went on a double date with a dump truck and a puma. Loads of tension on that episode. I think it was a two-parter.
Mountain building.
Ever wonder how mountains are built? If you haven't, take a second to ponder it. You won't have to wait long to find out if you're right. We're about to learn how mountains are built right now. Learn about a few different types of mountains, how they're formed, what it all has to do with plate tectonics.
Did you know the highest mountain on the planet rises over 29,000 feet off the surface of the Earth? The locals call it Sagarmatha, or Goddess of the Sky.
In English, this goddess of the sky is known as Mount Everest. Everest is part of the highest mountain range in the world, the Himalayas.
The Himalayan range runs east to west from eastern Pakistan through Nepal and all the way to Bhutan. Even though the Himalayas have been around for as long as you or I or any of our great-great-great-great-grandparents can remember, they weren't there forever. So how did they form?
As you can see, the range forms a sort of natural boundary between India and Tibet. This is an important clue to the mountain's formation. Can you guess what it tells us?
You see, India and Tibet are not part of the same tectonic plate. India lies on the Indian plate, while Tibet is part of the Eurasian plate. And, go figure, the Himalayan range lies directly on the boundary between these two plates.
Clever Earth scientists have pieced together the story of the Himalayas.
Turns out India and the rest of Eurasia were not always right next to each other. In fact, they used to have an ocean between them. Really? But then where in the world did that ocean go?
It sank. Over millions of years as the Indian plate moved toward the Eurasian plate, the oceanic crust at the edge of the Indian plate subducted or sank below the Eurasian plate. Slowly, the Indian continent closed in on Eurasia. Eventually, the two collided. Can you guess what happened next?
It's an epic battle of continent on continent. What will happen?
When the two continents finally collided, their crusts crumpled up against each other, causing the rock to bend upward into folds. Up, 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 that crust rose like it was trying to lick the butter off some great corn on the cob in the sky.
The Himalayas are an example of a type of mountain called a folded mountain. A folded mountain forms when a continental plate collides with another plate. Instead of breaking, the two plates simply bend or fold. Folded mountains make up some of the highest mountain ranges in the world. They are also the most common types of mountains in the world.
Ladies and gentlemen, please welcome the last deodorant-free dance troupe in America with their critically acclaimed epic movement drama, Push.
As we've seen, the Himalayas were formed at a convergent plate boundary. You know, a place where two tectonic plates collide. Most mountains are formed at convergent plate boundaries. Write that down.
You should know, however, that the Himalayas are a bit unusual. They were formed by the collision of two continents. That's what makes them so gosh darn high. It is more common for mountains to be formed when a piece of oceanic crust dives under a continent. You know, at a subduction zone.
A subduction zone, remember, is what you get at a convergent boundary where oceanic crust collides with continental crust. Because the oceanic crust is denser than the continental crust, it subducts or sinks or dives beneath it. Subduction zones usually occur at the edges of continents.
A good example of mountains created at a subduction zone are the Andes Mountains of South America. The Andes were built when the oceanic Nazca plate slid beneath the South American plate. This forced the continental crust to get shoved upward. As you can see, the chain extends down the entire western edge of the continent.
If you're having trouble visualizing this, just picture the way icing piles up in a mound on your spatula when you scrape it from the bottom of a bowl. This is similar to the way the continental crust gets shoved upward as oceanic crust dives beneath it.
You know, Subduction zones are also abduction zones. Don't be fooled. Every nook and cranny in those Andes mountains are crawling with little green men.
Let's just stick with the facts, okay? Let's get into a bit more detail about what exactly is going on during this whole mountain building process.
Right. Movement at plate boundaries puts rocks under stress. There are different ways that rocks can be under stress. Just what kind of stress? Well, rocks can be pushed together or they can be pulled apart. When rocks are pushed together, we call this type of stress compression. When rocks are being pulled or stretched apart, we call this type of stress tension.
There are a few different ways that rocks can react to stress. As we've learned, some rocks react to stress by folding, like this. This is how folded mountains are created. The rock bends but doesn't break. Not all rocks react like this, though.
Some rocks break under stress. When a rock breaks under stress, scientists call this break a fault.
Warning, do not confuse a fault with a plate boundary. Plate boundaries, as you know, are the edges of tectonic plates. Faults, on the other hand, are just cracks in the Earth's crust. Faults often occur as the result of stress caused by movement at a plate boundary. Check it out.
Movement along plate boundaries causes stress in nearby rock that may cause it to break. These breaks are called faults. Because they are often associated with plate boundary activity, faults often occur near plate boundaries, but they're not the same thing.
Sometimes mountains occur at faults. These types of mountains are called fault block mountains.
The Teton Mountains in Wyoming are an excellent example of fault block mountain range. Pack your cowboy boots, we're off to the Wild Wild West.
Tetons were created when pressure from below caused the crust to be forced upward or uplifted. This caused the crust to stretch out and ultimately to crack. Once the cracks were formed, whole chunks of rock were tilted upward as the uplift continued. This action created the jagged shape of the Tetons.
As you can see, fault block mountains are very different from folded mountains. Folded mountains are created when rocks are compressed together, while fault block mountains are created as the result of rock being pulled apart.
The thing about fault block mountains is they don't necessarily occur right at a plate boundary, but they are likely to be found near one. That's because the faults are often caused by plate boundary activity.
You're caused by plate boundary activity.
The last type of mountain we'll talk about today is called a volcanic mountain. Volcanic mountains are mountains that are formed through volcanic activity. Volcanic mountains are created at subduction zones.
When one plate slides down beneath the other, it melts into that hot layer beneath the Earth's surface, the asthenosphere. This allows magma to rise to the Earth's surface and erupt from volcanoes.
Let's review. Mountain building is the result of interaction between tectonic plates. Therefore, mountains tend to pop up at or near tectonic plates.
The most common types of mountains, folded mountains, occur at convergent plate boundaries, where two plates collide with each other.
Movement of tectonic plates puts stress on rock. This stress can come in the form of compression or tension. That is, rock being crunched together or rock being stretched apart.
When put under stress, some rocks bend and some rocks break. But all rocks need love.
One last thing. Mountain building can be pretty dramatic, but it's such a slow process that you could never watch in a theater. You'd be bored to tears. That's because tectonic plates move at rates of centimeters per year. The Rocky Mountains of the western United States and Canada, for example, have taken over 50 million years to get to their current heights.
But hop onto the grand scale of geologic time and you'll find that mountain ranges rise and fall as quickly as snow piles up and melts in your driveway. Earth is constantly shifting.
Volcanoes!
is the Ring of Fire? Is it A, a fiery portal leading from Connecticut to Jupiter? B, the part of the stomach responsible for digesting Tex-Mex? Or C, a zone of intense tectonic plate activity running along the perimeter of the Pacific Ocean?
If you answered A, you read too much science fiction. If you answered B, you're a good sport. And if you answered C, you're correct.
The Ring of Fire is an area of intense tectonic plate activity that forms a loop around the Pacific Ocean. This area runs through all of Southeast Asia and the Pacific Rim, across the Aleutian Archipelago and down the west coast of North and South America. More than half of the world's volcanoes can be found along the Ring of Fire. Not to mention, the majority of the world's earthquakes, including some of the world's largest earthquakes, have occurred here.
More than half of the world's volcanoes. Gosh, now the name Ring of Fire makes sense. But how did this happen? Why did this happen?
In order to answer that, let's learn a bit about volcanoes.
A volcano is an opening in the Earth's surface where hot magma and gases from the interior are able to pass through.
Please give a warm welcome to the Golden Chicken Project International, presenting Magma.
Let's take a closer look at the structure of a volcano. See this pool of magma deep underground? This is a magma chamber. Magma from the chamber rises up and exits to the surface of the Earth through these openings called vents. When magma reaches Earth's surface, we call this a volcanic eruption.
By the way, once that magma reaches the surface of Earth, it gets a different name. We now call it lava. It's sort of like if your name is Steve and then you graduate high school and your parents start calling you Peter.
That's Volcano Knowledge 101, people. But you want to know more, don't you? You want to know how volcanoes really work. So the next time you're at a roller skating party and a slow song comes on, you can confidently grab that special someone's hand, drag him or her out on the rink, and regale him or her with everything you know. No more hiding in the bathroom, and all thanks to volcanoes.
The key to understanding how volcanoes work is understanding what conditions are necessary for magma to form below Earth's surface.
Remember, Earth's surface layer is called the lithosphere. Just below the lithosphere, we have the asthenosphere. The asthenosphere is made of extremely dense, nearly solid rock. In order for a volcano to occur, some of this rock needs to get melted into magma.
Once the rock is melted, it has a lower density than the solid rock around it. This causes it to rise and potentially to cause a volcanic eruption.
Okay, but how does the rock get melted?
Shh, you're about to open up a can of worms. A chemistry can of worms.
Trust me, we don't want to go there any more than you do, but we have to take a peek in the can. Even if we don't open it all the way, hold your nose, it's only take a second.
Suffice it to say that for a rock to melt depends on three things: temperature, pressure, and what the rock is made of. For a rock to go from a solid to a liquid or even to a gas requires a change in pressure or temperature or both. The exact change required will depend on just what the rock is made of.
So that's the gist on how to melt rock. You need a change in temperature or pressure. So now the question is, how do changes in pressure or temperature occur? Or better yet, where do changes in pressure or temperature occur?
Changes in pressure or temperature occur where all the other drama on Earth occurs. No, I'm not talking about Hollywood. I'm talking about plate boundaries. You know, those points where two tectonic plates meet and interact. That's how the Pacific Ring of Fire ended up being such a hotbed of volcano activity. It's literally a ring of plate boundaries.
Volcanoes tend to occur at two types of plate boundaries in particular: subduction zones and divergent plate boundaries.
A subduction zone is a type of convergent plate boundary where one plate slides below the other. A divergent boundary is where two plates diverge or move away from each other. Divergent boundaries usually occur on the ocean floor. When two oceanic plates move apart from each other, a sort of underwater mountain called a mid-ocean ridge is formed.
Have you noticed that both subduction zones and mid-ocean ridges occur in the ocean? That means the majority of volcanoes on Earth happen under the sea. You know, in the deep, at the bottom of Davy Jones' locker, in the abysmal brine.
Subduction zones and mid-ocean ridges are both areas that are ideal for magma creation. Check it out.
At a subduction zone, water seeps into the asthenosphere, causing a change in temperature. At a mid-ocean ridge, the lithosphere is thinner because it's being pushed apart. The thinner layer puts less pressure on the asthenosphere below. Both these conditions can lead to the creation of magma and the creation of a volcano.
Ever wonder how volcanic islands are formed? Like we've said, most volcanoes happen under the sea. As lava from repeated volcanic eruptions piles up, submarine volcanic mountains are formed. When these mountains rise up to the surface of the ocean, that's how volcanic islands are formed.
Let's return to the Ring of Fire. See all those islands? Think of them like the dots to exclamation points. Well, upside down exclamation points. The point is, those islands are indicators of some pretty exclamatory business going on below.
Say, what about the Hawaiian Islands? They have lots of volcanoes, but they're in the middle of the Ring of Fire. Are they even on a plate boundary? What am I missing here?
Well, I read from a comic book that the Hawaiian Islands are all that's left of an ancient world called Lemuria that sunk into the ocean a long time ago.
Not exactly. The truth is the Hawaiian Islands are nowhere near a plate boundary. They were formed as a result of something called a hotspot.
You're a hot spot!
Hotspots are areas of volcanic activity that cannot occur at plate boundaries. Although scientists are not entirely sure how hotspots are formed, one theory is that they come from columns of hot magma rising from the mantle.
The theory goes that hotspots stay in the same place even as tectonic plates move over them. That's why they often result in long chains of volcanoes, as with the Hawaiian Islands.
Volcanic eruptions.
Let's talk a little more about volcanic eruptions. Remember, an eruption just means that magma reaches the Earth's surface. It doesn't necessarily mean a destructive, newsworthy explosion.
Basically, eruptions can be either explosive or non-explosive. Most of the time, they're non-explosive.
Non-explosive eruptions are when lava calmly flows onto the surface of the Earth. Explosive eruptions are not so chill. Explosive eruptions are the ones that make the news. They can cause massive destruction and casualties. Luckily, they're pretty rare.
So what makes an eruption explosive?
The same thing that causes most explosions. Gas!
When magma breaks through the surface, whatever water or other compounds it contains suddenly turns to gas due to the release of pressure. The super fast expansion of the gas that occurs at this moment can cause an explosion.
Let's make this simple. Basically, a volcanic explosion is like what happens when you shake up a can of soda and then open it. The sudden release of pressure causes the pent-up carbon dioxide to spray all over the place.
What comes out of a volcano when it explodes? Explosive eruptions mostly produce something called pyroclastic material. This is simply hardened lava. It forms when magma is blasted into the air.
Volcanic ash is one well-known form of pyroclastic material. When the Icelandic volcano Eyjafjallajökull erupted in 2010, it belched enough ash into the sky to disrupt European air traffic for weeks.
And now for the question we've all been waiting for. How can you predict when it... And now for the question we've all been waiting for. How can you predict when an explosive eruption will occur?
Well, unfortunately, it is difficult, if not impossible, for scientists to predict exactly when a volcano will erupt. However, they can collect data that will help them determine the likelihood that a volcano will erupt at a given time.
For example, by mapping old lava flows and studying pyroclastic deposits in nearby rocks, scientists can keep track of a volcano's past eruption record. They can then use this eruption record to predict future eruptions.
Scientists are also able to make pretty good predictions about when an active volcano will erupt by listening to the sounds it makes.
If you live near a volcano, rest assured, at this point, scientists are able to provide much more warning for volcanic eruptions than for, say, earthquakes.
Earthquakes.
What are we looking at here? Is it A, a gnarly scar on the stomach of the great desert sand monster? B, a tear in the Earth's surface caused by tectonic plate movement? Or C, part of an ancient landing pad for UFOs?
If you answered A, you've been spending too much time with your nose in a fantasy novel. If you answered B, you're correct. And if you answered C, you'll have to come with us.
Don't think I don't know about the landing pad. I know the truth!
What you're looking at here is an image of the San Andreas Fault in California. The San Andreas Fault is notorious for having been the cause of some pretty destructive earthquakes. That includes the 1906 earthquake, one of the worst natural disasters in the history of the United States.
Oh no! It's an earthquake! So what is an earthquake? An earthquake is when the earth quakes.
Duh.
Oh no! All right. Most earthquakes originate from faults, like the San Andreas Fault. A fault is just a crack in the Earth's crust. Faults are created when rocks are put under stress, like, say, you stretch your t-shirt out so much that it tears. It's the same idea.
But where does all that stress come from? Why can't the rock just chill out?
Why don't you just chill out?
Dude, I'm roadkill. How much more chill can I get?
Usually the stress is caused by the movement of tectonic plates at plate boundaries. You see, faults are often found near plate boundaries. The San Andreas Fault, for example, is near the boundaries between the North American plate and the Pacific plate.
Okay, I don't want to talk smack or anything here, but are we noticing a pattern? Every time there's drama on Earth, it always goes back to those tectonic plates. For real.
For real. Every time these plates shift around, this puts more and more stress on nearby faults. This stress is setting the stage for an earthquake.
Rocks under stress have a tendency to bend or to break. Scientists call this deformation. But not all deformation leads to earthquakes.
When rocks under stress simply bend into a new shape, this is called plastic deformation. Plastic deformation does not lead to earthquakes.
Other types of rock are way more uptight. These rocks will stretch as far as they can without breaking, but eventually they will snap. Just like your mom freaking out after she tells you for the 5th time to clean the hermit crabs out of the microwave. Yeah. Scientists call this elastic deformation, when stressed rock stretches as far as it can before snapping back into place. Elastic deformation does lead to earthquakes.
Elastic deformation causes rock to snap back into place just like a slingshot. This snapping is called elastic rebound.
The snapping motion of the rock is what causes an earthquake. Actually, that snapping motion is the earthquake.
When the rubber band of a slingshot is let go of, energy is released. That's how the slingshot works. It's the same with elastic rebound. When the rock snaps back to its original position, energy is released.
This released energy travels through the Earth in waves called seismic waves. When we feel an earthquake, what we are feeling is the undulation of these seismic waves. The magnitude or size of the earthquake is determined by the size of the waves.
Ladies and gentlemen, please welcome the Foes of Toes Dance Company for their final performance of the controversial piece, Elastica.
Let's review. How do earthquakes happen?
Earthquakes happen at faults, places where stress put on the rock has caused it to crack open. Further stress causes the rock to deform. When rock is stretched so far that it suddenly snaps back into place, this snapping motion causes an earthquake.
Earthquakes occur at or near all different types of plate boundaries. Plate boundaries, remember, are the places where two tectonic plates meet and interact.
Earthquake safety.
An earthquake zone is an area where earthquakes are common. In other words, an earthquake zone is a place where there are lots of faults.
If you find yourself in an earthquake zone, you'll need to be prepared for the zombie apocalypse. Once an earthquake occurs, the zombies will crawl out in force from the bowels of the earth.
For people in zombie zones, earthquake zones, a common question is, when will the big one hit? Minor earthquakes happen all the time in earthquake zones, but big ones tend to be few and far between. As more and more time without a big one goes by, one of two things begins to happen. Either people completely forget that it is even a possibility, or they get so paranoid that they start spending all of their time sharpening machetes.
Predicting earthquakes is a tricky business, and here's why. Plate tectonic processes have been going on for millions of years. They operate on geologic time. So, scientists might be able to say, for example, that an earthquake at the San Andreas Fault is likely to occur sometime in the 20th century. In the grand scheme of geologic time, that's pretty darn specific. But for us humans, it's not very practical.
That's why if you live in an earthquake zone, it's important to be generally prepared, but not paranoid.
Make yourself a zombie kit. You'll need an armored car, some good footwear, and a few tubes of toothpaste. And remember, earthquakes may be hard to predict, but zombies are never your friends.